Okay. Oh, just a second, I'll change the...
Okay. Dear colleagues, today we have a talk of Gesualdo Scutari from Purdue University. Aldo spent a lot of time and think a lot about the relation of machine learning, optimization, and in my opinion, this is one of the most interesting direction in modern optimization, how to use the specificity of machine learning problems and developed method that use this specificity. This is very interesting direction, especially in decentralized optimization. And in my opinion, Aldo, at the moment, one of the maybe most active person who works in this direction. And it's my great pleasure to announce his talk at our seminar. This is really very valuable event because we have a very good opportunity to learn about this topic, and I very hope that some students are interested in this direction and start to working in this direction, because as I have already been mentioned, this is very perspective direction. Okay, Aldo, you can start.
Okay, thanks, Alexander, for the nice words and the introduction. So it's a great pleasure for me to be with you today. And yes, as you mentioned, as Alexander mentioned, I would like to share with you today a slightly different perspective than traditional distributed optimization. And I mean, I've been working on distributed optimization for several years, but mainly from the optimization point of view. Today, I would like to focus on distributed optimization, but with an emphasis on algorithms explicitly designed for machine learning problems. And in particular, the class of machine learning problems that go under the name of, that are captured by the discipline known as high dimensional statistics, and which is the hardcore of several so-called big data problems. I mean, the typical regime of high dimensional statistics is the one where the ambient dimension is even larger than the data, and we are interested in understanding the statistical and computational guarantees when both the dimensions and the data are, the number of samples are very, very large, with dimension even larger than the data. And think of problems like sparse estimation of low rank factorization of matrices and so on. And in particular, my emphasis in this talk will be on statistical and computational guarantees. And the message that I would like to share with you, even if my results are very preliminary, some of the work is still unpublished, is that if we really want to characterize and understand statistical and computational guarantees of distributed algorithms in this high-dimensional regime, we need a new theory. The existing, don't read me wrong, there are a lot of results in the literature of distributed optimization, and many of you, I mean, Alexander's group also contributed a lot in this context. But my message is that these results are most of these results are of pure optimization type. They don't capture the statistical component, and which means that they are not enough to understand the behavior of distributed algorithms in this high-dimensional setting, because they don't capture some phenomena that happened there. And hence the title of my talk, that bringing statistical thinking in distributed optimization. So let me, before going to the details, let me give you the background. And for those of you who may be familiar maybe with distributed optimization, the context is the following. We want to learn, make decision and optimize so-called networking data. So data that are basically stored and acquired locally at different nodes in a network. And examples are, there are many applications like that, starting from the traditional applications 20 years ago on sensor networks, or more recently, for example, technology like edge computing, where the idea is to move the intelligence of the system at the edge of the network. And the idea here is that you have heterogeneous devices that can talk to each other, and also with the cloud. or more traditional, let's say, federated learning like systems where the goal is more to parallelize the computation because you have still multiple machines possibly connecting through a node, a center, and the goal is to speed up the process with parallel computing. And in particular, in this talk, I will focus on application where the computational architecture is the so-called mesh network. Basically, that looks something like that, in contrast with the more traditional architecture that you can find in federated learning, that leads to the traditional ones, where you have a centralized node that can talk to all the other nodes in the network. Here, the network that instead we are considering that are also known as mesh networks are networks where each node can only has part of the data and can only talk to a subset of the nodes that are connected through a link in this graph. And the goal is to, our desiderata would be designing algorithms that can achieve the same statistical and computational guarantees that you have in this set, where you have a node that can access to all the information. And generally, that standard approach to do that, given that every node here can only talk to some neighbors and there is no centralized node, the traditional approach when it comes to design distributed algorithm is to embed, interleave in the design, optimization, local computation steps where agents solve locally some sub-problems, and communication steps where agents exchange information with their neighbors to update their local information that they need to move to the next iteration. And in general, when it comes to do the design, understand the behavior of this algorithm, characterizing the performance of these algorithms, there are trade-offs involved. And the traditional approach in optimization is to study pretty much computation and communication trade-offs, so the standard complexity analysis and so on. In this, when it comes to machine learning problem, I would like instead to consider a broader picture and to incorporate also statistical error. So by statistical error, I mean generalization errors when it comes to training neural network, or estimation error when you want to estimate a parameter and so on. And the question becomes, for example, a typical question is, what is the statistical error that I can achieve if I have a finite computation and communication budget? And I think it's fair to say that our understanding of the full trade-offs, the three components in the distributed optimization for machine learning is very limited. On one hand, we have a lot of knowledge about the behavior and the performance of distributed optimization schemes, meaning that we know how to compute the rate, we know lower bounds, and we know how to accelerate that. But all these results are of pure optimization type, meaning that they have only an indirect impact on the statistical trade-off or the statistical aspect of this trade. On the other hand, so which means that if you look, it's like to say that we know the understanding of this trade-off only on some axis, right? On the other hand, if you look at the stat part, there have been recently a lot of works trying to understand the statistical and computational trade-offs in the centralized optimization. But however, they lack of they lack of the networking component, which is the other dimension. This dimension will introduce new phenomena that are not happening in the centralized setting, meaning that these works cannot capture the full trade-off here. And for example, a typical regime that is not present in the centralized setting is the one where locally agents may have not enough data, may not have enough data for statistical consistency. But if you look at the data across the entire network, you have enough data to achieve good estimate. The question is that, can we still then achieve centralized statistical guarantees in this setting when data locally are not enough? And if so, at which communication cost? So these are all, another important open question is, what about scalability with respect to dimension, with respect to the sample size, and with respect to the number of agents? And what's the role of the network, the topology, into these trade-offs? So all these questions are, in my opinion, open. And the approach that we need to follow in order to address this question is to combine at more fundamental level these three aspects: the computational aspect, the statistical component, and of course the networking component. And that's my take-home message, if you want, a very high level of this talk, and also a message for students who approach this topic for the first time. And of course, I don't have an answer to all these fundamental questions, But I want to, in this talk, I want to give you the flavor of what we can achieve if we change a bit our way of thinking and we bring this statistical thinking in our analysis. And in particular, I will focus on this fundamental question. Can we centralize statistical errors on a network? And if so, at which computation communication cost? Meaning that I'm not really capturing the entire trade-off. This is an open problem. I'm fixing the centralized error that I want to achieve. I fix the statistical error, in particular the centralized one, the same that you can achieve in a centralized system. And I'm asking what is the cost of the communication to achieve and computation to achieve this centralized statistical error, if it's possible. Okay, that's the key question that I want to address in this talk. But before doing that, let me start with the existing theory. Let me explain what I call our non-understanding of even very simple problems. Okay, so I'll show you now what we can predict with the existing theory, and I show you that basically with a simple vignette example, that the existing theory is not enough to understand what happens in the high-dimensional region. Okay, feel free, by the way, to interrupt me anytime if you have questions. Okay, the problem the example that I will consider is very simple. It's just a linear regression problem over a network. What do I mean by that? I mean that we have M agents that are in a network that are basically connected through a graph, undirected graph fixed, and every agent takes measurements, wants to estimate a parameter theta star. This parameter is a sparse parameter, so which means that this parameter has only S component different from 0, and the entire dimension here, D, ambient dimension is D. And what we do is that every agent here gets some measurements, yi, a subset of the entire measurements of this parameter through a linear model, right? And in particular, agent 1, for example, will observe a linear, the parameter theta star through this linear transformation, and W is the noise. And every agent owns only one subset of data of measurements. Okay, so this data, the vector of measurement, the data metrics are owned by each of the agents. Okay, that's basically the problem. And let's consider a very simple estimation of this parameter, the so-called lasso, for example, estimation. Let's consider the lasso estimator in the projected form. And the optimization problem looks like this. So we want to estimate our star via a parameter theta hat, which is the solution of this very well-known problem, a projected lasso problem. You are projecting on the L1 ball of what? Of a quadratic loss, right? And this problem, I mean, what makes this problem different from the standard centralized optimization is the fact that you can interpret now each term of this sum. Actually, let me write it up here. Each term of this sum as basically the local loss of agent I. And so this looks like the sum of all the losses of each agent. And in particular now, the challenge here is that every agent knows only its own function Fi, because every agent has access only to its own data, not the data of the others. Okay, so the question becomes how to solve this now on a network. And in particular, that's the thing that you may want to keep in mind for the rest of the talk, is that we are interested in the so-called high-dimensional regime. What do I mean by that? We want to capture a big data scenario. So we have a lot of data measurements, but the ambient dimension D can be even larger than the data. And this high-dimensional scaling is a scaling where we assume that both N, the total number of data in the network, and D, the ambient dimensions, are both growing, okay? And meaning that the problem becomes more and more complex, D grows, and also the number of data samples are growing. And in a way that the number of the dimensions can be even larger than the data. So this ratio can go to infinity. And we want to understand what are the scaling properties of D and N in order to make statistically consistent estimate. We can make the estimation error small, and we can compute this estimate. So this is the question. These are the questions asked by the so-called high-dimensional statistic field. Okay, keep in mind, this is the regime we are interested in. Okay, Again, if there is any question, note that this is different from the traditional so-called low-dimensional statistics, where you assume d fixed, so you are fixed the model, and you are sampling from this model, so n goes to infinity, d is fixed, so basically this ratio is going to 0, and you want to understand when you have more data, how well are our estimation, for example. This is the standard traditional low-dimensional statistics, right? Here we are in the high-dimensional regime, where both d and n are growing. Okay, if that's the setting, what do we know about this problem from a statistical and computational perspective? From a statistical perspective, this is a well-known problem, and it doesn't matter if we are solving this problem over a network or not. We have a lasso problem, and we want to understand the statistical property of this theta hat if someone will give us theta hat. Okay, and this is a well-known problem under very standard assumptions on the regularizer and the data distribution. We know that with high probability, this problem is learnable, meaning that with high probability, if I use theta hat as a proxy of theta star, the statistical error, so the gap between the parameter that I would like to estimate and what I can get, is controllable. And it's controllable by this ratio. This is the important result. This says that basically the regime we are really, if d divided by n is going to infinity, as long as s log d divided by n is small o1 is small, we can control this error. We can make this error arbitrarily small. So this tells us that the regime we are interested in this setting is the case where the dimensions d are growing and also n, the ratio is going to infinity, but n is of the order of s log d, okay? Keep in mind this. This is pretty much the regime we are interested in. We are interested in, yes.
May I ask a question? What is about variance? Because I guess this result should depend on the level of variance.
This is with high probability. This is this is no. This results in the projected lasso. The results does not depend directly on the variance. The variance will, because I mean, this is the Lagrangian version. Yes, you are right. This is also the variance of the noise. In this, there are some assumptions here on the statistical. The noise is Gaussian. With there are some assumptions here, and I'm hiding the dependence of the variance. I consider the variance fixed in this case. So you are right. It depends on that, but I'm interested here in understanding because I assume that the variance is fixed. Because what I'm interested here is more the behavior of this error with respect to these parameters for now. But yes, the variance of course will affect, but I assume that the variance is not, it's absorbed into the big O.
Okay, I see. Thank you.
Sure. But the interesting, so keep in mind this, we are in a situation where d divided by n is going to infinity, but if the number of samples scales logarithmically with the dimension, we are guaranteed that the statistical error can be made small, is controllable, it's roughly constant in this regime. What happens? This is based on the assumptions that someone will give us theta hat. How can we compute this in practice? So on a network. So let's look at the problem now from an optimization perspective and see what the existing distributed optimization theory tells us about the computation of this theta hat in this regime. Okay, keep in mind then this regime. Okay, from a computational perspective, what do we have? Look at the problem just from a pure optimization. This is my problem. What I observe is that this function is, first of all, is convex, but it's not strongly convex. Because we are in a regime where d is larger than n, so the Hessian is d by d, but the rank of this Hessian is n, which means that you have, if you look at the landscape of this function, it looks like flat in some direction, right? And carved only in some other direction. What about the Lipschitz constants of the gradient? If you look at the Lipschitz constants of the gradient under a standard probabilistic model of this data matrix, basically we see that the Lipschitz constants of the gradient, which is the largest eigenvalue of the Hessian, will scale like d divided by n. And if you look now at this, you will observe that you see this d divided by n is going to infinity, which means that basically the Lipschitz constant in this scaling, asymptotic scaling, is growing, which is a kind of negative result, because in general, the Lipschitz constants will affect the step size, right? The step size will be related to the inverse of the Lipschitz constants, meaning that when the Lipschitz constant is growing, if the Lipschitz constant is growing, the step size is going to 0, which means that your algorithm is slowing down. So based on this property of the landscape and the existing theory of distributed optimization, I think we can roughly, very high level, say the following: that given that the problem is not strongly convex, but only convex, existing distributed algorithms can achieve only, can solve this problem at sublinear rate. In order to have linear rate in general, you need strong convexity in a global sense. Any question? Okay. So first, we have sublinear convergence, and the other important component in the regime where basically we are considering, even if the number of samples is basically let's assume even big O. So when the number of samples scales like this, we know that the statistical error remains pretty much constant, is not changing, but the rate at which we are computing our theta hat is going to 0 because of the issue that I mentioned about the Lipschitz constant. So this seems to be the end of the story with the existing theory, because we identify a regime, this high-dimensional regime, where statistics tells us that there exists statistically consistent estimate, because this quantity can be small, but even if D and N are growing, but even this quantity remains constant, in order to compute this theta hat, I'm computing with a rate that is going to 0. So these statistically consistent estimates are not computable in practice efficiently. I mean, with a rate, with a constant. We would like to have what? In a regime where the statistical error is not changing, we would like to have a rate that is not changing as well. Okay, that's the big gap, what the theory says. Now, given that the theory didn't really exploit the statistical part of this problem, let's see how effective are these predictions in practice, meaning that let's simulate some of the existing algorithms, and let's see if we can match these predictions, what the theory is telling us. Okay, and let me start from simple simulations. Let me simulate a very well-known old algorithms. It's basically one of the first attempts to decentralize the projected gradient algorithm, which is the so-called distributed gradient algorithm that I'm reporting here. Just for those of you who may not be familiar with this algorithm, let me explain briefly what this algorithm does. Basically, in this scheme, we have multiple agents, let's say agent I and agent J in particular. And given that we are minimizing, if you remember, we are minimizing with respect to this common theta, the sum, 1 over m, of these functions phi theta, right? And given that every agent knows only its own function, we cannot solve this on a network directly. We need to decouple these functions. And the standard approach in general to decouple this function when it comes to distributed optimization is to introduce local copies like theta I and theta j for each agent that are updated iteratively. So we are at time t here. And the way to update iteratively in these local copies in this specific distributed optimization scheme, it's quite simple. You see what this does? There is an optimization step, this one, that is nothing else than a local gradient, projected gradient. With this notation here, I'm denoting the projection onto the L1 ball. Every agent that is sitting in the local copy theta j is doing a move along its own local gradient. So for example, this agent is going to move this way along minus its own local gradient. And this will generate an intermediate point, this guy here, this point here. And same story for this other agent. Suppose that it's moving in, for example, in this direction. And this is the intermediate point based on its own gradient, Fi of theta it. And then after that, every agent does that in parallel. And then every agent, then this information is communicating to all the neighbors. And at the receiver side, each agent I will determine the new update, just doing a convex combination with this W, these weights of the information coming from the neighbors. And this is what is called consensus step. The idea here is that you want to make sure that you need to enforce some alignment along this local copy, because every agent is moving only along its own gradient, and then this will not solve the original problem that I want to solve, this problem here. So the idea is that after a local update, you do a consensus, a complex combination, so you try to meet halfway, and this will determine basically the new, this will determine the new update theta I t plus 1, and if you want theta j t plus 1. So, and then after that, the idea is that you do another step of gradient like this, and then you keep going. Okay, that's what this scheme does. It's a very simple decentralization of the gradient using only the local information that you have, your own gradient. Okay, how does it work? And this algorithm works according to this theory, right? Because this theory captures also the behavior of this algorithm. So what happens if I simulate this scheme in the high dimensional set? Let's look at the numerical results. What I plot here are, remember, this is the, I have a bench. First of all, let me show that, let me tell you what I plot here, what I have in the card. First of all, I have the statistical error as a benchmark. This is the best we can do, right? It's the centralized statistical error, which is this black line over here. This is the best you can achieve, right? Given the data that you have. And so let's see how our algorithm, distributed algorithm works with respect to this benchmark that we want to achieve. What I plot is the error between the iterate theta of each agent and the ground truth. This is not the solution of the empirical risk. It's not theta hat. This is theta star, it's the ground truth, the parameter that we really want to compute. So I take the square error of each agent, and then I take the average. This is the quantity that I'm plotting over here, okay, versus the number of iterations. See what happens. And different curves here will refer to different step size gamma. Remember that in the gradient algorithm here, there is a step size gamma. And basically here for different step size, I have different curves. And in particular, as you can see, let's look at the behavior of this curve. This curve shows that basically linear, but not to an arbitrary error. This not linear rate up to an error that can become arbitrary small. No, linear rate up to an error that basically you see up to a floor. And this floor depends on the step size, meaning that if you decrease the step size, gamma, if gamma goes to 0, this floor will go down. So these different floors are achieved for smaller and smaller step size. And as you can see, if I keep reducing the step size, eventually I will achieve the centralized statistical error. But to do that, I'm losing on the rate, because you see that this is the linear rate, and then for a given step size, if I decrease, it becomes slower and slower. So we observe, so the first results that we observe is that we have linear rate up to a ball, to a tolerance, and there is this speed accuracy dilemma, meaning that if I want to achieve a centralized statistical error, assuming that these are achievable, at least in this experiment, it seems that they are, we need to slow down our algorithm. And so this contradicts with the existing theory that predicts sublinear rate. Okay, there's already a gap between theory and practice. What about the scaling? Remember, we are in a regime where D and N are going to infinity, but we use the number of samples sufficient for statistical consistency. So in this regime, the statistical error is fixed, it's not changing. And I would like that also the rate of convergence will not change, because yeah, so that no matter if the problem becomes more difficult, if I have enough data, the statistical error is controllable. I would like it also there is no change. Okay, let's see what happens in the scaling. I plot here the same quantity, the estimation error that I showed in the previous picture versus the iteration for different dimensions. So D is growing. As you can see here, I'm going from this value here and then to larger value. And I'm in every time I change D, I also change the samples in order to satisfy the property to have an almost constant statistical error. And as you can see, and I plot here the error, the iteration, the optimization error for the centralized proximal algorithm for these three different D values. As you can see, the rate is almost invariant. So, and also the statistical error is of the same order. Remember, these are Monte Carlo simulations, so there is some randomness, of course. But if you look at DGD, the distributed counterpart, you can see, the rate is no longer invariant. You can see better in this other curve where I change the scales to show you can see better what happens to the DGD. So we have this issue here about the fact that we cannot compute efficiently the solution, even if the statistical error is not changing. And there is, by the way, no theory to explain this kind of behavior in the high dimensional regime. now a natural question is that, okay, is this a limitation of this specific, because we have this undesirable behavior, right? The question is this a limitation of the specific algorithm we have, this projected DGD, or this is common also to other distributed algorithms? The distributed optimization literature is plenty of other schemes that we can use. And well, if you look at the other algorithms, here is a snapshot of some of the vast literature on distributed optimization. We have, for example, schemes that are, don't worry if you're not familiar with this scheme, I will, in the second part of the talk, when I go into the technical details, I will comment some of this scheme. Here are just some, let's consider some snapshots, some samples of some examples of distributed algorithms, just to see what happens. And as you can see, these are the where I show the estimation error versus the iteration. And for three different, I guess, two different dimensions, 10,000 and 1,000 and 10,000. And the behavior is very, I wouldn't say random, but it's very different from algorithm by algorithm. For example, this algorithm here, Sonata, has the property that seems that it is rate invariant, even if the dimensions are changing. Remember, here the samples are scaling like this. The rate remains invariant, and roughly it converges to roughly the same statistical error. But if you look at other schemes like PG Extra or DGing, they go from the projected version of the scheme of DGing. You see, when D is equal to 1,000, you have this rate. When D becomes 10,000, they break down dramatically, and we don't understand why. Why is that these algorithms in the low dimensional regime, basically the strongly convex case, when the number of data is larger than the dimension, they behave roughly the same. They are good, I mean, these schemes. How can be in the high dimension, some schemes work and some others are not? So, and we don't understand why. So that's the big picture. So we need a better understanding and a different analysis of the schemes in the high dimension. And maybe this will also help to design new schemes. And the question is that why is this happening? What are we missing? So let me try to explain what is the underlying phenomena that we need to understand in order to fill this gap between theory and simulations. And this is pretty much the outline of the technical part of the talk. I will first go a bit more into what is the statistical phenomena happening here that it's not captured by the existing theory of distributed optimization. And then I will, once we know what's happening, we'll try to use this understanding to refine the analysis of the existing schemes. And in particular, for pedagogical reasons, I will focus on one of the schemes in details. And then, but it's interesting, then I'll show you what happens to the other schemes. I may not have the time to go into the technical details, but I'll show you a summary. This is very interesting because there's a surprise that you may not expect of what's happening or what happens in the high dimension, given what we know already in the low dimensional case. Okay? Any question, any comment so far? Is it clear what we want to, where we want to go?
Yeah, please, questions?
Okay. Okay.
I guess there is no question. Okay, thank you.
Okay. Okay, so this is a joint work with some of my students, and Yao Ji in particular is my PhD student, statistics and optimization, my postdoc, Marie Maros, and my former postdoc, Ying San, who is now an assistant professor in the US here. And in particular, this work is based on, this presentation is based on 3 works, but I'm very sorry not all the papers are available online. I really wanted to share with you these very new results, but I'm still working on some of the papers. One paper is available, the analysis of DGD, in particular DGD CDA. You can find this paper on arXiv. The analysis of the second paper that I'm going to talk about, this gradient tracking, is this second paper that is going to be available hopefully next week. I'm finishing really writing now the paper. I will post it online next week. And in any case, you can write to me and I can send you the preprints if you cannot find it online next week. I mean, it's really, and then there is a third paper that I will mention later to show where the third paper, basically, which part of that paper will cover of this talk. Okay, right. Let's try to understand what's going on here. So we learn from statistics, we know that under some assumptions, the statistical error is controllable through this ratio. So this is a kind of typical result that happens in the strongly convex case, right? When the error between the population and the empirical in terms of objective value is small, you can transfer this error on the argument, right? On the variables. In general, in order to do that, you need strong convexity, right? But in this case, we don't have strong convexity. So how is the case that then we can still establish these results? The reason is that if you look at this error, what we call the statistical error, this vector here, the difference of these two guys, this is a vector of dimension D. But remember, we want to estimate a theta star who has effective dimension S. Only S component, which is much smaller than D, are basically the non-zero component. So the idea is that the key fact here is that even this vector technically is a D-dimensional vector. In practice, this vector will belong to a lower dimensional space. Basically, will belong to a space of which I will call space of, actually it's a cone of sparse directions. In other words, mathematically, what we can observe is the following. Let me explain with the picture first, and then I will give you the math. So suppose that, let's call S the support of theta star, is the set of components of theta star that are non-zero. And S orthogonal, S complement is basically whatever is outside the support of S. Let's assume 2 dimension here for simplicity. So the vector theta star belongs to this space, right? This is where somewhere here, where theta star belongs to. Now, theta hat, which is instead the solution of the lasso problem, if the regularizer is sufficiently small, it's not exactly sparse as theta star, otherwise this error would be 0, but it's roughly sparse. It's close to theta star, so it's close to this space. This will mathematically is captured by the fact that then the error belongs to this cone that tells you how far theta hat can be from theta star, from this subspace, okay? And the cone, in fact, if you look mathematically more closely, is the set of all the directions such that the amount of mass outside the support, this is the projection, the mass, the projection of the delta into the outside the support. So the number of, this is a measure of the amount of mass outside the support, is smaller than the mass inside the support. So this is a sparse direction, okay? And this can be proved mathematically in 3 lines. You just need to study the geometry of this problem. It's very simple. I will skip the proof, but it's really 3 lines. It's just triangular inequality and optimality condition. And so this means what? That if the lasso error, this error here, belongs to this cone, we don't need the function f here to be strongly convex everywhere. We only need the function to be convex in this cone. So we need this function to be convex only in a restricted set of directions that are basically into this cone. And if this is the case, that's the key property that we need in order to establish this statistical guarantee. And this is exactly what happens. Under a general model, data generation model, I assume here Gaussianity, but Gaussian is also okay for both data and noise. Basically, what we can prove is that the lasso function, so this function here, with high probability satisfies these 2 conditions. Let's look at this condition in detail and see what they are. They are nothing else than, at high level, this is a notion of restricted strong convexity and restricted smoothness. And this wording is very similar to the one used in optimization as well, with a slightly different meaning. But let's look at this inequality. This is the quadratic form along the direction delta of the Hessian associated. It's the quadratic form associated to the Hessian of the function, the objective function. This objective function is a quadratic function. So if you look at the first part here of this inequality, this would be the standard definition of strong convexity, right? The minimum eigenvalue is bounded away from 0. By the way, sigma is the covariance matrix of the data. And this would state standard strong convexity property of the population, of the empirical risk minimization, which is not the case here. So what we have instead is we need to relax this condition, and we add a tolerance, this negative term. And what this says is that in the direction where this quantity, the right-hand side here, is strictly positive, this inequality is enforcing a curvature, right? It's saying that the function is roughly, this is basically strictly positive. So we are capturing basically this direction, the directions where you are carved. But in the directions where this quantity here is negative, this inequality is vacuous. So it's not saying anything. So these are the directions where you're flat, okay? That's the way to, and by the way, what are the directions where you're curved? Where basically are the directions where basically this quantity is positive, meaning what? Meaning that basically we are controlling the L1 norm of this quantity by the L2 norm, okay? When this ratio is small. And similar property here for the smoothness, right? Again, the first part here would be the standard definition of L smoothness, is where the Lipschitz constant will be related to, of the gradient will be related to this quantity, but we don't have that. We have a relaxation where basically we have this tolerance there, okay? And this is called restrictive smoothness. Keep in mind one quantity here that I want to highlight, because this will play a key role later, is we can define similarly to what we do in standard optimization when you have strong convexity and smoothness, we can define in this relaxed setting a restricted condition number. Let me call restricted condition number, kappa, which is just the ratio of basically the largest eigenvalue of the covariance matrix and the smallest value. Basically, if you have an infinite number of samples, so meaning that the empirical will converge to the population, which is strongly convex, because I'm assuming the covariance matrix is positive definite. Basically, when these terms are basically negligible, both of this, basically this will be the traditional condition, is the condition number of the population. So we can interpret for a finite number of samples, big N, this like a restricted condition number. The condition number restricted to the direction where the function is strongly convex. And this will play a key role in understanding the behavior, the computational guarantees, the behavior of the convergence rate of our distributed algorithm, okay? And it's not difficult to say that, to check that if the number of samples here is sufficiently large, you can, and you use the fact that the directions are in this cone, you can prove easily, it's just one line, that if you lower bound that basically this property, for example, implies standard strong convexity into the cone of sparse direction. This is also known as restricted eigenvalue property, okay? So basically we know that with high probability, it's true that the function is strongly convex only in a restricted set of directions, and same for the smoothness property. Given this property now, I think that it's clear what we would like to do. We know that the function is strongly convex and smooth and L-smooth in a restricted set of directions, sparse direction, this cone C that you see here in the picture. If we want that our algorithm will experience a fast convergence, we need to make sure that we need to design or tune the degrees of freedom of the existing algorithms in a way that the trajectory of the algorithm will stay as close as possible inside this cone, so that basically the algorithm will travel along directions where your function is carved. And hopefully this will experience roughly a strongly convex and L-smooth function with some error, some tolerance, okay? That's the idea, what we would like to do, which is missing in the existing analysis and theory. But the idea is very simple. The execution, however, poses some challenges. First of all, the question is that are the trajectory of, because different distributed algorithms are based on different ideas of constructing the direction, right? The direction along with each local copy is updated, right? The algorithm is moving. And different directions now, if in the strongly convex case, when you are strongly convex everywhere, maybe the directions will matter, of course, but you do strong convexity if you move in the wrong direction. In this case, the issue is, this is a more sensitive issue because different algorithms will move along different directions, and it's not clear that all these directions are compatible with the cone C, meaning that it's not clear that given an existing algorithm, just tuning the free parameters, I'm able to make sure that the trajectory is confined into the cone that I want. And in fact, that's the surprise, not surprise, that's the key part. What we show in in this sequence of papers is that actually there are some algorithms that cannot, whose trajectory cannot be controlled to stay within this set. And this will determine their bad scalability or their bad behavior. But even if you can control this trajectory, if you potentially can control this trajectory to keep it inside this set, the second question is that how can I enforce this property in a distributed way, given that locally agents do not have access to the entire landscape of the function. And more importantly, what's the role of the network in all of this? Are there some topologies that are more favorable than others? And also how the performance will scale with the samples, because the more samples I have, the closer I will be to a fully strongly convex function, because the empirical will converge to the population loss. But so, and what is the role of how much communication do I have to spend in order to rebuild maybe locally this global landscape to understand how to control the trajectory? And yeah, these are all open questions in the distributed set. I will try to answer this question for a specific algorithm. I'll go a bit into details of the result. And then I will explain what happens to the others. I may not have time to go into the details or all the details, but maybe if there's time at the end, I will show you also some new technique that we are using to prove these results. In order to give you a first result, I will focus on one of the algorithms that we introduced a few years ago, which is based on the idea of gradient tracking. And we apply this to the projective lasso problem. So I remind you that this is the problem that we want to solve on a network. And here, the main issue is the fact, as I mentioned, that every agent does not know the function of the other. So computing a full gradient of this is not possible locally. So the idea is to estimate this gradient at every iteration. In other words, every agent in the computation step, every agent has a local copy theta I of the global theta, the global theta variable. And the idea here is that every agent will perform first a projected gradient step onto the L1 ball, but instead of using the real gradient, the gradient of this function, which is not available, is going to use a proxy, an estimate. This GI is an estimate of nabla F. And nabla F, this is my F, okay? It's an estimate of the full gradient. So every agent locally first perform this practice step with this noisy gradient. And then there is a consensus step where every agent will just do a convex combination of the local copies of its neighbors to align this local copy. And then I need to build a mechanism to estimate, to update these GIs in order to be an estimate of the full gradient. And this can be done with this step. It's known as dynamic consensus mechanism. Basically, what this scheme does is very similar to a consensus scheme, but there is a time varying signal embedded into this update, because we need to track the gradient nabla F that is not a constant quantity, but is changing over the time. And I will not go too much into the details of this scheme. This is a scheme that is today is well known. What this does is quite simple. Every agent will have its own local estimate of the gradient. What it does at every iteration is to send to the neighbors the following quantity: its own local estimate at time t plus updated with the new gradient that I just get given the theta j, the update that agent performed. And then I add the new gradient, I subtract the old information. This quantity is passed to the neighbors, and every agent at the receivers will update its own local copy, just doing a convex combination of all this quantity received from the neighbors. And we can prove that if, together with the consensus mechanism, basically this quantity will track the gradient, in the sense that the average across the agents of this quantity is equal to the average of the gradient. So I mean, this is a well-known, this has been studied in the literature. So, but at this stage, keep this like a noisy gradient that computed in a distributed way. So what are the performance of this scheme now in the high dimension, given that we need to use this we need to develop a new theory to be able to capture this behavior. Here's the main result that we have. And the results is the following. We have some assumptions. Under the same statistical assumptions that we have in the centralized setting. So basically random data, sub-Gaussian, basically IID, this can be sub-Gaussian, even the noise can be sub-Gaussian. And remember, this is the condition, the restricted condition number that I used before. Remember what I did. It's basically the condition number of the covariance matrix. You can, roughly speaking, think of this like the condition number of the population loss if you have infinite number of data. And under the assumption of statistical consistency, this assumption is unavoidable. This is also the assumptions that guarantees that the statistical error is small. So this has nothing to do with the network, has nothing to do with our specific distributed scheme. This is a condition that has to be satisfied also in the centralized case. And then under a condition on a network that I will get back to this in a minute, this condition says that the network should combine information sufficiently fast. I will clarify this in a minute. Let's hold on. I mean, let's discuss this in a minute. So under these assumptions, if you consider the iterates generated by the algorithm, you will see that if I consider the average of the square errors of each iterate from the centralized, from the ground truth, this is the ground truth, not the empirical minimization solution. This is the parameter that I really want to estimate. This quantity will shrink linearly with this rate lambda, but not to an arbitrary error. The error cannot go to zero. Error will this will shrink linearly up to a tolerance here that I will clarify in a minute. Let's see now. So basically what this says is that the algorithm will converge linearly, not to the solution theta star, but to a ball around the solution, okay? And let's look closely at the rate and at the ball to see what kind of optimality we can claim here. Because we cannot compute exactly theta star. So the question is now to understand if this ball is of the right order or if it's too large. Okay, first of all, let's look at these two quantities, the rate and the ball. The rate, lambda. Look at the rate. The rate has this basically structure. And if you look closely, this term here, this is very similar up to a constant to the convergence rate of the projected gradient algorithm applied to the population problem. So if you have infinite number of samples, because remember, kappa is the condition number of the restricted condition number. The rate that we get here is not exactly that, because we are not strongly convex everywhere, but there is a degradation of this rate, which is, however, given by the C prime is extra constant, it doesn't matter, which is basically due this rate, there is a degradation of this order, S log D divided by, given that this S log D divided by N is small, this rate is roughly the rate of the centralized proximal gradient algorithm, okay? And because of, and this is, if you can interpret this degradation on the rate that is small under the assumption that we are under statistical consistency, and this is the price to pay from the fact that you are not exactly strongly convex everywhere, but you are restricted strongly convex and small. So we learned that basically we have a rate very close to the centralized gradient algorithm. Remember, this scheme is not accelerated, so this is pretty much the best you can get in this specific setting where you are not accelerating. And what about the ball, the tolerance that we have? Well, the good thing is that this tolerance, it's exactly of the order of the statistical error, which means that statistically, this is the best we can hope for, because computing a solution, an effect of theta star below the statistical noise makes no much sense. And this ball is exactly of the order of the statistical noise. Okay, so this tells us an important thing, that if you look at the problem combining statistics and optimization, you will learn that you don't need to reach from a pure statistical precision just looking at the problem from a pure optimization perspective. But you need to consider the statistical error as well, even in the distributed setting, so that you can compute. What this says is that you can achieve linear rate, fast rate, up to the statistical precision. Below that, I cannot tell you anything, but it doesn't matter because we are below the statistical noise, okay? And what about, and the other important question is, remember the regime that I was mentioning, N and D are going to infinity with D divided by N blowing up, and but with the condition that the number of samples, the ratio S log D divided by N is small. If you want, this can be small O1. And in this setting, the statistical error is not changing. What about the rate of this algorithm? The good thing is that if you look at the rate depends exactly on this ratio. So as long as this ratio is fixed and the network is fixed, there is the rate, the good property here is that the rate remains invariant. It's not changing with even if the problem becomes more complicated, and of course the samples are growing accordingly to what statistics is suggesting us. okay? And this is confirmed by our simulations. This is an example of basically the rate invariance, meaning that I plot here the estimation error, basically this quantity here, versus the iteration, and for different dimension d. And as you can see, if we scale the samples according to the theory, and here m is the number of agents is fixed, so it's growing, the local sample size is growing to achieve this property, to satisfy this condition. And as you can see, the rate, remains pretty much invariant for these three curves, and you achieve pretty much the same order of statistical error. What about the, any questions so far?
I guess no questions.
Okay. Feel free to interrupt me anytime. I don't know.
Okay.
By the way, how much time do I have, Alex? Because I think that maybe I'm running out of time.
I don't know, say 20, 30 minutes.
I thought I had only 1 hour. Okay, so I have more time. Okay, I can then dig a bit more into some details. Okay. What about the property that I was mentioning about the network property, this one? This condition is basically, this row is basically is related to the mixing property of the Markov chain associated to the weight matrices. Basically, in other words, roughly speaking, is, if you want, I can give you the definition. This is the operator norm of the matrix W of the weights minus the total, the projection of the consensus space. This measures basically how fast the network is mixing information, so how fast the consensus error, all the disagreement across the local copy is shrinking. And the smaller, this is a number between 0 and 1, and basically 0 if you are fully connected, and 1 if you're not, and then the smaller, the faster the mixing, okay? And what this says is that the network should scale inversely to the basically polynomial of the number of agents and the restricted condition number. So if the problem becomes more difficult, so kappa is growing, is large, then rho should be small. And this to some extent will tell us something about how the network should basically, remember, this is not a full trade-off. We are assuming that we want to achieve the centralized statistical error, which is what we are assuming, what we are achieving here, even with a rate that is very close to the centralized proximal gradient implied calculation. So what's the price that we have to pay to achieve that? How good this tells us the network should mix information sufficiently fast if your goal is to achieve the centralized statistical error with a rate that is close to the centralized proximal gradient. And now, what happens if this condition is not satisfied? Because if you can design the network, freely, maybe you can enforce this condition. But what happens if this condition is not satisfied? Well, this is a very standard, well-known. By the way, first of all, before mentioning that, the first question, another question that I forgot to comment that I would like to make here is that is this condition an artifact of our proof, or we really need this condition? Note that these conditions are all sufficient. So I don't have, unfortunately, a lower bound to show you mathematically to prove how tight they are. And so what I can tell you is that maybe the coefficients here are not tight, maybe the order of the polynomial is not tight, but what I can show, at least numerically, is that the condition is unavoidable. We need the condition, rho cannot be constant. And this is what we can show. Rho should go to 0 when the number of agents are growing or when kappa is growing. And this is unavoidable. Otherwise, you can no longer achieve the centralized statistical error. And this is what this curve shows. If I show this experiment to check if this condition, is necessary or not to some extent, at least numerically, and what you can see is that this is the centralized statistical error, and I plot here this quantity here, the left-hand side, and versus the iteration for different. And here I'm changing the number of agents, so the number of agents is growing, and I'm changing the graph. This is a graph. I'm changing the graph in a way that the connectivity remains constant, very small, but constant. So it's not going, it's decreasing with m. And as you can see, when m is small, so that this condition is roughly satisfied, as you can see, we can still achieve the centralized statistical error a linear rate. But in the moment that you start increasing m and rho remains constant, at a certain point, this condition here would be violated here because m is going to 0 and rho remains constant. And in the moment that you violate it, as you can see, you can no longer achieve the centralized statistical error. Your algorithm is breaking down. If you ask me what is the magic scaling that you need on rho with respect to m, it seems that the magic scaling is 1 over square root of m. And this is what this simulation shows, that basically if you change the graph in a way that the number of agents are growing, and rho is, the topology is changing in a way that the rho scales like 1 over square root of m, as you can see, the rate remain invariant, and you achieve for different number of agents the same centralized statistical precision. Okay.
Alda, could you please remind what is rho? I guess this is a previous slide.
Yes, rho is basically this quantity. W is the weights. If you remember, the algorithm has a set of weights here. These are the weights that you use for consensus. So you can build a matrix W where you have, let me do that. So Wij is basically, is your Wij here, these weights. So if you put all these weights here into a matrix, there are some structure, some property in this matrix with the graph is connected. So this matrix is basically doubly stochastic because I assume that the graph is undirected and is irreducible. So there are property that will tell us that this matrix has eigenvalue between -1, not included in 1. In the moment that I write this, sorry, where is it the matrix?
Am I right that the condition you obtain that rho should decrease like 1 square root of m means that when m is growing, we have almost full graph. I mean, connection network.
Yeah, you can. Yeah, you need to increase. Yeah, you need to increase with. Yes, you are making close to a graph that can become eventually. If you consider that, the graph will become more dense. Yes, I show you. If you give me a second, I'll show you some topology that will satisfy this with a bit more detail. But yes, you're right. You need the network that if you have more agents, because think about that. We are in a regime, Alexander, where there is something interesting. Big N is fixed. Big N is the total number of samples, right? Which is equal to the number of agents times the local number of samples. So this is the local number of samples. And this is the number of agents, right? When you increase...
small n is the same as small s. Small n is the same as small s before or not?
No. Small s is the sparsity, n is the small n is the the local sample size.
Okay.
So
okay,
this is the number of agents. So n is the total samples across the net. So in this regime, m is growing, as you can see here. N is fixed. So which means that we are in a regime where the local sample size is going to 0. So this is a regime that you don't have in the centralized case. So it's a regime where locally the agents will have less and less samples, although the total number of samples across the network remains constant. So eventually the number of samples is going to 0. So the only possibility to be able to achieve the centralized statistical error is that, of course, the network will help, right? To mix information sufficiently fast. There is no way that you can avoid. If you fix the centralized statistical error, remember, this is not a full trade-off. We are targeting the centralized statistical error. And the question is that, what is the price that we have to pay if you want to achieve that? Okay. Another question is that if you don't have a network so good, what can you achieve? And how far you are from the centralized statistical error? These are open questions. Okay.
Okay.
Yeah, and how to enforce this condition on a network if you don't have a network that by design satisfies this? This is a very well-known trick. You need to run multiple rounds of communications per gradient evaluation, right? And this is the total number of communications that you need per iteration. This tells you that if you put everything together, so linear rate, number of iterations, and local number of communication of this order, so that basically this condition is satisfied, you end up with these results. And this is the total number of communications that I need to reach to converge to an estimate of theta, to converge to an epsilon neighborhood of a statistically optimal estimate theta star of theta star. And this number of communications is basically depends on, this is the traditional thing that you have in the strongly convex case, right? The condition number, restricted condition number, and the network effect, 1 divided 1 minus rho. And then you pay a log factor on the number of agents. And basically, as I show you, this seems to be unavoidable if you want to target centralized statistical error. But the good thing is that this number does not depend on the dimension. So in a regime where the network, when D is divided by n is going to infinity, but S log D divided by n is constant, this rate remains invariant, okay, if the network is fixed. And this is a good property. You have a question, Alexander?
Yeah, I see. Thank you.
Yeah. Okay. What about, maybe I can skip. Yeah, I had also some, because now that you have this rate, you can understand how the topology will affect, because topology appears through rho, and maybe I can skip this for interest of time. There are different topology. This is well known. There are different bounds for this ratio here. And depending on the graph, you can have a different scaling with the number of agents. And so I have a kind of characterization here of how the different topology, what is the total communication cost, depending on the topology for different graphs. Maybe I can skip this because I'm just using the formula that we obtain here and existing results to characterize this quantity here, 1 minus. So this is I'm not adding anything new to this discussion in terms of novel technique or results. So I'm just using then results from the literature to close the loop, and given our new formula, I'm just interpreting the formula. But I can skip this for the interest of time, because I want to use the time left to give you a sense of what happens to the other algorithms. Because I show you a detail for this, but what about the other schemes in the literature? There are many schemes in the distributed optimization setting. And what about now the behavior, the provable behavior of the schemes using this new theory that capture this restrictive strong convexity and smoothness? And there are several schemes, so I don't have the time to go into the details of all of them, but I'm picking here a selected list of algorithms based on, I would say, the family these algorithms belong to. In other words, we saw before this scheme, right? We saw the DGD. In particular, now I can tell you a bit more about DGD because there are different versions. This version is called adapt, then combine. Why? Because what this scheme does, if you remember, you have two agents, theta I here, T, let me see, focus on two in particular, theta J. What this scheme does is to first move along its own gradient, projected, this term, and then what it does is to do a convex combination with the neighbors. So it does something like this so that you generate the new update, theta I, T plus 1, and theta J, T plus 1, right? And then they move to another directions, wherever this direction is, and so on, right? This is called adapt, then combine, because you first adapt, you first move along your own gradient, and then you combine the information. On the other hand, by contrast, there is another scheme in the literature that is called combine then adapt. So you can do the other way around. So you can, if you have here theta, let me move a bit this down. So the other scheme, the CTA, the combine and adapt, does the other thing. This is theta IT, this is theta JT. So they first, the information, as you can see here, so they first get closer, and then they move along their own gradient. They correct using their own gradient, okay? So this is called combine then adapt. And so these are different ways to, you first use some local information, then use consensus to align the local copies and correct the error due to the fact that you're not using the exact gradient, the gradient of the total function, global function. There are, Sonata is the scheme that I showed you before, use a different philosophy, the idea of correct the direction. In this scheme, sorry, gradient schemes, they use the step size, they have to use the step size to control the error coming from the fact that you are not using exact gradient, but you are using a local gradient. In the literature of distributed optimization, of course, consider also other schemes where the idea is to try to not delegate the step size to control this error, but to introduce a mechanism to estimate, to have a local estimate of the global gradient, rather than using only your local gradient. Sonata, the scheme that I showed you before, is an example of that method that does this in the primal domain. Just use a gradient tracking mechanism. But there are a lot of other schemes. I don't have time to go into details of all of them. For example, another approach is to do a primal dual that is based on a subtle point reformulation of your optimization problem. Most of you, I guess, are familiar. This is just one guy of this family. It's not, of course, does not cover everything, but I just wanted to give a sense of this primal dual method, where the idea is, you see, you do a mixing like you are doing in CTA. You first mix the information with the others, and then you correct. This is the gradient, the direction that you are using. But now this direction, as you can see, has not only your local gradient, like for example, in the CTA scheme, but there is also a correction of this direction with the dual variables, so that you try to not use only your local. And the dual variables are updated according to the standard dual update, okay? So this is just one member of the family of this primal dual. What's the behavior of this algorithm in the high dimensional regime? In the low dimensional regime, these primal dual work quite well. And what happens in the high dimensional? What's the effect of these different actions, right? Combining and adapt, combining first and then adapt, or adapt first and then combine, or correcting in the primal domain, or correcting the dual domain. These are, when you are strongly convex everywhere, these schemes work decently well in the low dimension. But when the direction matters more, because in some directions you lose strong convexity, we will see that the behavior of these schemes in the high dimension can be drastically different from what we expect from low dimension. And this is exactly what happens. This is what we have here. Let me comment these results one by one. And then I'll tell you, I don't know if I have time, maybe I'll tell you a bit about the theory that we developed to understand the behavior of the scheme. We developed a unified framework, and maybe I can just say a few words of this now. We extended the idea of stability of algorithms, which is well known in the stochastic setting, low dimension. We extended first to the high dimensional setting and then to the distributed setting. That's the theory that we are developing. We needed a new theory in order to understand the behavior of this algorithm. But let's see what happened to this behavior, because there are some interesting results here to comment. Okay, remember, the goal, I want to achieve a solution that is in a neighborhood of a statistically optimal solution, okay? To be in an epsilon neighborhood of a statistically optimal solution, a centralized statistically optimal. That's the goal. If you want to achieve that, what happens to the rate of these schemes? Okay, in the DGD CTA, remember, is this one. You first combine and then adapt. It happens that if you want to achieve a centralized statistical error, the net will help to achieve that. But in order to do that, you need to choose the step size in this way, meaning that you need L is the Lipschitz constants of the population, and basically you need to choose the step size that scales inversely with dimension. This means that the step size is going to 0 in the regime where, remember, we are in this regime. In this regime, the step size becomes smaller and smaller when in this asymptotic scaling, if you consider this scaling when D is going to infinity, which means that your algorithm becomes slower and slower. And in fact, if you count for the total number of communications to achieve this statistically optimal solution, this is what you get. The number of communications will grow linearly with dimension. And this is a kind of negative result. And that we already observed at the beginning in some of the simulations for the DGD-like scheme. And this result is this scaling of gamma. That, again, this is a sufficient condition to achieve centralized statistical precision. Let's say, we have numerical results validating this scaling, meaning that this condition seems to be unavoidable in order to achieve centralized statistical error. And this is what this curve shows. This is an example where it shows that if the dimensions are growing and you scale the step size with 1 over D, as you can see, you can achieve centralized, you can still achieve centralized, always centralized statistical error, but your rate is going up. So the number of communications are growing. Now, what happens if you, the question now is that, do we need a scaling of the order of 1 over D, or we can tolerate a slower scaling, right? And what this curve shows is that no, the scaling has to be 1 over D. This is unavoidable if you want centralized statistical error. And this is capturing this curve because what I show here is that on the y-axis, the limit point the statistical error in at the convergence when I terminate the algorithm. I don't remember the precision that I set here, versus the gamma, versus the step size gamma. And as you can see, as long as gamma and this line for different dimension, different plots here refer to different dimensions, D and N. And as you can see that, and this dashed line down here is the centralized statistical error. And this bar here, vertical, tells me the value of gamma satisfies the scaling 1/d. As you can see, as long as gamma satisfies the scaling or goes to 0 faster, you can achieve the centralized statistical error here, here, and here. In the moment that you break the scaling, your the statistical error that your limit point will achieve is basically no longer matching the centralized one. You are breaking this fairly close to this 1/d, okay? What about the DGD ATC? What about the other mixing? So remember, CTA first mix and then correct the direction of the local gradient. What about the other way around? You first move using your local gradient, then you mix both iterates and gradient. That's the key thing. If you do that, you can free the step size, meaning that the step size can now be chosen independent on the dimension. And by the way, this is the restricted, this is the restricted strong convexity constant, and this is the restricted strong convexity smoothness, smallest and largest eigenvalue of the covariance matrix of the data. And you can achieve this, but you can achieve centralized error with a step size that does not scale with D, but you need a network sufficiently connected. So the difference with the CTA is that no matter how good is the network for CTA, there is no hope that CTA allows us to achieve, to have a rate that does not scale, that is independent of the dimension. With the ATC, we have a slightly better dependence because we have the network that has to scale with 1/d, which translates in a total number of communications that it scales only logarithmically with the dimension. So it's slightly better than linear with the dimension. And this is a consequence of the fact that the kind of mixing, I will comment this at the end after this last algorithm. And then look at the primal dual. This is the surprise. Well, it's the surprise maybe at the beginning before studying the scheme, but afterwards maybe there is an interesting interpretation. The primal dual scheme behaves as bad as CTA. Basically, the step size in order to achieve centralized statistical error has to scale inversely with the dimension. And this will give me a linear dependence of the total number of communications on the dimension. And so this is kind of surprising results to some extent, surprising up to some extent, because if you ask me, and then you have, of course, Sonata, our scheme that is independent of the dimension. So this is a kind of ranking of these algorithms that you see in the high dimensional regime. And now, why is that? I mean, if you ask me an interpretation of this result, I would say that the reason is that what we learn from and by the way, again, these results are kind of tight in the sense that I have also for the others, I don't show for the interest of time. If the scaling does not satisfy this condition numerically, you are no longer able to achieve centralized statistical error. Actually, for some scheme like this ATC and so on, the algorithm can diverge. Okay. What's the take-home message here? Why do we have this behavior, this different behavior, drastically different behavior between CTA and ATC or primal dual versus primal method? If you want my interpretation, the reason is that if you look at the scheme here, let me clean a bit here. If you look at the scheme, the reason is that conceptually, the CTA scheme is very similar to what the primal dual does, because in the primal dual, you are mixing the iterates, like here, like you're doing here, but you are never mixing the gradient. You see, the gradient is a correction that you do afterwards, after mixing. And unfortunately, the gradient is the one that is not sparse. So if you don't mix the gradient, you are introducing an error that scales like D divided by local sample size. And that's the problem. That's why you need to use a step size to control this error in order to achieve centralized statistical error. Otherwise, you achieve an error that is, if you, the analysis in this negative case, but you can no longer achieve an error that is instead of the order of log D divided by N. Okay, so what we learn is what seems to be true here is that in order to achieve centralized statistical error and have a good scaling of the communications with the dimension, possibly independent, you need to mix both iterates and gradient. You cannot mix only the iterates. And actually, this will suggest us new schemes. In fact, I will not present it now, but in the paper that I'm going to post on archive, not the second one, the third one that will happen hopefully in January, when we develop this unified framework, you will see also new scheme based on this new understanding that we have of these algorithms. And I think that with this, I can maybe wrap up and conclude this talk. And where basically I show you how we need to have to combine more statistical, to incorporate more statistical thinking in our traditional distributed optimization schemes. It's true that whenever you have a problem, even machine learning, that looks like sum of phi of theta, you can have distributed optimization. But my message is that be careful, because there is much more than that in many problems. There is more structure and coming also from statistics. And if you want to have a better understanding of the behavior of these algorithms, you need to incorporate the statistical analysis into your distributed optimization analysis, right? And I show you just a few algorithms, and I show you a first attempt towards this direction where we can try to fill a gap between theory and simulations, but there are a lot of things to do. For example, now we are developing in my group the concept of acceleration in the high dimension. This is a completely new direction, because acceleration, you cannot use the standard acceleration in low dimensions, because that would depend on the Lipschitz constant in the low dimension, which scale with, remember, d divided by n, which means that this will go to infinity. A traditional acceleration in the low dimension is not going to work. And same story, or what about the trade-off, I mean, between statistical error, computational communication. Here, I didn't really, I didn't have the entire theory, the Pareto curve, right, of all this trade-off. I only fixed the statistical error that I wanted, and I try to understand how much we pay in terms of communication and computation. But the other part of the trade-off is still not clear. And what happens when you have heterogeneous data, for example? There are a lot of open questions in the moment that you basically open this Pandora box and you try to understand in this high-dimensional regime the behavior of distributed algorithms, incorporating this statistical thinking. And yeah, and with this, I think I can stop. I mean, thanks for your attention. I hope that I gave you a sense of what this direction looks like.
Gesualdo, thank you very much. Now, please, questions. Okay, may I try to ask your first question? So if we consider initial problem formulation as stochastic optimization problem, this problem will be strongly convex, because we have assumption about covariance matrix. And if we solve, if we solve this problem without decentralization, it was not a problem to obtain so linear rate to the convergence to some Vicente that corresponds to the variance. I mean, it is well known in common non-distributed optimization such a result.
Yes, of course. Yes.
Stochastic algorithm converge linearly to some Vicente that determines by the variance. If variance is small enough, this Vicente is small. And it is well known for non-accelerated algorithms.
Yes, and it's what basically, I agree. It's basically, if you want to give a statistical flavor to these results, there is a paper of Martin Wright and Eigenvalue that basically do that. So it's what I'm citing here, right? This paper over here, and I think that I have here, is this paper here that in the centralized optimization, these results is known. Yes.
I see, but the same result we can find nowadays almost at all papers, because typically modern papers write as follows: algorithm converge to some Vicente, and this Vicente depends on the variance. But all these algorithms non-accelerated. And there exists...
No, but Alexander, the question, yes, that's true. But my question is that, are you really in the high dimensional regime? That's my question. Because in the low dimensional regime, it's very clear. I agree, you have the variance, but the variance would be of the order of square root of d divided by n. And this will be a bad error. You have to be careful. This is well known, but it's low dimension. You are assuming d fixed, basically, and and n going to infinity. This is the, yeah, I agree. This is a well-known, this is the traditional statistical analysis in the low dimensional regime. Now, this is the variance that you're talking about. In fact, this is also based on, there are a different way to prove that. For example, the stability, right? In the stochastic magician, there's the stability analysis, right? It does exactly that. You center around the covariance, exactly like you're saying, and you have a linear rate on the term related to the trajectory of the applied to the population. And then you have an error that is of the order, let me find a place where I can buy, is of the order of the difference of the two errors, right? It's of the order of the gradient of the, let me call n the population, right? A t minus the gradient of the, this is the gradient of the empirical risk, depending on samples. And this is, let me call p the population, right? The expected value, t. And this is the error that you are talking about, the variance. And if this quantity in the low dimension is exactly square root of d divided by n. So if you use this analysis, you can prove linear rate, but you prove linear rate to an error ball of this order, will blow up, which means that this result is completely unusable in the high dimensional setting when d divided by n is going to infinity. This is exactly the issue. So you cannot use standard results that you're mentioning to do this in the high dimensional regime. You lose the, you need to, and the problem is exactly this, Alexander, this is a very good point. And that's the new analysis that we developed when I said that we extended the concept of stability in the high dimension. The problem is that in the traditional analysis, what do? You try to characterize this error, which comes from using the triangular inequality, right? And you upper bound with this error. The problem is that you cannot do that. In the high dimension, this error is not sparse because the gradient may not be sparse. What is sparse is only the direction. So you need to consider this error that I wrote here, not in any direction like the traditional analysis does, considering the norm, but you need to project this difference along sparse direction, considering the inner product. That's what you need to do. You need to understand this minus theta star, inner product, nabla L of theta t minus nabla L of theta t. So this inner product is the quantity that you need to understand in the high dimension. And this can scale with, eventually will give you other errors, but the dependence would be of the order of log d divided by n. That's the key part. That's the new analysis you make.
Very interesting. Yeah, it's a significantly new point because I have previously.
Exactly. It's that's why I was excited to share with all of you, because this opened a completely new. Even acceleration becomes more difficult now because you need to be very careful. I mean, with all these terms. I mean, and in particular, you cannot break this inner product using just Cauchy-Schwarz or wherever, and then reduce to this error and do the standard analysis that you center around the population, like you're saying, with the covariance, and then treat the variance error term. You cannot do that because the variance would be a variance in all the directions. But in all the directions, you are not sparse. You're only sparse in some subset. So if you do all directions, you get this, which scale like square root of d divided by n, which is not good. You need to keep the projection along the sparse direction. This is a sparse direction.
I see.
And you need to project the error. You need to understand the variance, if you want, along the sparse direction. That's the tricky part.
But this analysis significantly use the specificity of the problem that is lasso problem type. Or
no, very good point. We have we started from the lasso for the quadratic case because the Hessian does not depend on the points. We'll simplify a bit the analysis, but we can extend. We have done the full extension. We are working on that. I have one student working on generalized linear problems. I think that for generalized linear models, I think that it's doable, and this will match completely the state of the art. Because that's what this, we can do generalized linear model. We can also consider regularizers that are weakly convex, not necessarily convex. So as MCP, SCAD, all these kind of non-convex regularizer that are weakly convex are still fine.
Okay.
So
and
we can do.
And one regularizer is significant in this analysis to obtain to deal with.
Yeah, but we can also do. We have also results. The paper that I mentioned, one of the papers that's already on archive, consider the Lagrangian version. So still the L1, but Lagrangian version. So we can go beyond L1. We can do SCAD, MCP, these other regularizers, but you need something that promotes sparsity, right? Because if you solve the empirical minimization in the high dimensional regime, you don't have sparsity, you don't have an implicit regularization. So you need to enforce a regularization. So you need some form of sparsity. It may not be L1, you can do more sophisticated regularizers, but you still need a regularizer.
I see. Very interesting in my opinion.
Thanks. I'm glad that, again, if any of the students is interested, I will be happy to discuss also with you, Alexander. We can discuss offline.
But I should read more because as far as I understand, this is a significant new things for me, I guess for students too. This is very interesting. Okay, really.
Yeah, I wanted to send a different perspective, right? Yeah, I hope that you like it. It's still preliminary, but I mean,
Okay, I know your November paper. I plan to read this paper next week maybe, and I hope that I will write you an email about this.
I can also show you, maybe we can schedule a meeting later, because that paper is ad hoc analysis specifically for that scheme. Now I have this unified framework based on stability that is more general. It goes beyond the specific algorithm. We didn't study Sonata, and basically for these two schemes we did for Sonata, and for this scheme here, basically this one, my pen is not working. For this one here, this is the paper of November. Sonata is the paper that I'm going to send out next week. But then for the other schemes, I developed a unified framework based on the generalizing the concept of stability, even in the centralized case, it was not known, based on the problem that I was telling you about these variants, right? And that paper would be available maybe later in I need a month to finish the paper. We have the results, but I need to wrap up. For that one, maybe I can share with you more details offline if you want. After you read the paper, maybe we can talk.
Okay, very interesting. And I guess we can obtain your slides also in January, when your archive paper will be submitted.
Yes, of course.
Okay, I remind you about this, because we typically upload slides on our website of seminar.
Sure.
It is useful for students.
Sure, let me just send out this, because as you can see, this part, to my knowledge, is completely new. So I would like to post on archive for something. Otherwise, this is really, I mean, there are a lot of results here that are nowhere. So.
Yeah, I completely agree. This is very new view, a new, how to say, this is new understanding of how we can post the problems. This is very interesting in my opinion. Thank you.
Thank you. I'm glad that you like it.
Yeah, I'm really like it. Yeah, very interesting. Maybe another questions.
Sure.
Colleagues? Okay. Thank you one more time, and
thanks to all of you for having me with you. So thank you.
Thank you very much, Aldo. Thank you. Goodbye.
Bye.